Welcome to Cambridge IGCSE Physics, Lesson 45.1, Magnetic Field Around Wire. This lesson covers core content from the Cambridge International General Certificate of Secondary Education Physics Syllabus, Specification 0625. Today we explore the fundamental relationship between electric current and magnetism, specifically how current flowing through a straight wire creates a magnetic field pattern around it. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, describe the pattern of magnetic field due to current flowing through a straight wire. This means understanding the circular field lines that form around the wire. Second, know the direction of magnetic field lines. Direction is crucial in physics and follows specific rules. Third, use the right-hand grip rule correctly. This is a practical technique for determining field direction. These objectives align with Cambridge IGCSE assessment, focus on core understanding and practical application of electromagnetic principles. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, magnetic field, which means a region of space where magnetic forces act on magnetic materials or moving charges. The field exists around magnets and current-carrying conductors. Second, field lines, which means imaginary lines that show the direction and relative strength of magnetic fields. Closer lines indicate stronger fields. Third, right-hand grip rule, which means a method for determining magnetic field direction around a current-carrying wire using your right hand. Understanding these terms precisely is crucial for mastering electromagnetic concepts. Let's explore our first core concept. The fundamental principle states that electric current produces a magnetic field around the conductor. This discovery by Hans Christian Ørsted in 1820 revealed the connection between electricity and magnetism. The key features are, first, the field forms circular patterns around the wire, with the wire at the center. Second, field strength decreases with distance from the wire, following an inverse relationship. Third, direction depends on current direction. Reversing current reverses field direction. We measure current in amperes, symbol A, and magnetic field strength in Tesla, symbol T. The diagram shows field lines as concentric circles around a wire carrying current into the page, indicated by the cross symbol. Now we examine the right-hand grip rule, a practical method for determining magnetic field direction. This follows Cambridge IGCSE requirements for understanding field patterns. The method consists of 4 steps. First, point your thumb in the direction of conventional current flow. Conventional current flows from positive to negative terminal. Second, curl your fingers around the wire as if gripping it. Your fingers naturally curve in the field direction. Third, your fingers show the direction of magnetic field lines around the wire. Fourth, this works for any wire orientation, vertical, horizontal, or diagonal. Remember, always use your right hand, never your left hand. This rule is universal and works worldwide. The diagram shows current flowing upward through a vertical wire, with circular field lines following the finger direction. Let's work through our first example. The problem states, a straight wire carries current of 2.0 amperes northward. Describe the magnetic field pattern. We are given, current equals 2.0 amperes, direction equals north. We need to find the field pattern description. Step 1. Apply the right-hand grip rule. This is our primary tool for field direction. Step 2. Point thumb north following current direction. Conventional current flows from positive to negative. Step 3. Curl fingers around the wire. When viewed from above, fingers curl clockwise. Step 4. Field forms circular pattern around wire. The pattern is concentric circles. The answer? Circular field lines, clockwise when viewed from above, with current strength 2.0 amperes determining field intensity. Example 2 examines how field strength varies with distance. The relationship shows that field strength decreases with distance from the wire. Let's analyze the key points. First, the strongest field occurs closest to the wire. At the wire surface, field strength is maximum. Second, field weakens as distance increases. This follows physical laws of field distribution. Third, the relationship is inverse. Doubling distance significantly reduces field strength. Fourth, larger current creates stronger field at all distances. Current is directly proportional to field strength. The practical implication is that field effects are most noticeable near the wire. The graph shows this inverse relationship clearly, with field strength dropping rapidly as distance increases from the wire center. Advanced applications involve multiple wires and field interactions. When several current-carrying wires are present, their magnetic fields combine according to vector addition principles. For parallel wires carrying current in the same direction, the fields reinforce between the wires, creating stronger combined fields. This causes the wires to attract each other due to magnetic forces. For parallel wires carrying current in opposite directions, the fields oppose between the wires, partially cancelling each other. This causes the wires to repel each other. For perpendicular wires, complex field patterns result where the circular fields intersect. Vector addition determines the resultant field direction and strength at any point. These principles apply in electrical installations and electromagnetic devices. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, wire carries 3.0 amperes eastward. What is the field direction above the wire? Use the right-hand grip rule to determine this. Question 2 is intermediate level. It states, 2 parallel wires carry current in opposite directions. Describe the interaction between the wires. This requires you to apply field combination principles. Question 3 is advanced level. The question is, explain why field strength decreases with distance from the wire. This tests your understanding of field physics. For all questions, remember to use the right-hand rule consistently, show you're working clearly, and include units where appropriate. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how today's concepts apply in practice. In electromagnets, coiled wires carrying current create strong, controllable magnetic fields. The circular fields from each wire loop combine to produce powerful electromagnets used in scrapyards, magnetic resonance imaging, and maglev trains. In electric motors, magnetic fields from current-carrying wires interact with permanent magnets to create rotational motion. This converts electrical energy to mechanical energy in countless devices. In transformers, changing currents create varying magnetic fields that transfer energy between circuits at different voltages. Career-wise, these principles lead to electrical engineering, designing power systems and electronic devices, renewable energy technology, developing wind and solar systems, and medical technology, creating diagnostic and treatment equipment. Let's review the solutions. For question 1, using the right-hand grip rule, point thumb eastward following current direction, curl fingers around wire. Above the wire, fingers point southward, so field direction is south. For question 2, when currents flow in opposite directions, the magnetic fields oppose between the wires. This creates a repulsive magnetic force causing the wires to push apart. The field lines are compressed between wires, creating higher field energy that pushes wires apart. For question 3, as distance increases, the magnetic field spreads over a larger circular area. The same magnetic energy distributes over greater space, reducing field strength at any point. This follows inverse relationship with distance. Exam success tips. Always draw diagrams showing field patterns and current directions. State which rules you're using, such as using right-hand grip rule. Explain the physics behind your answers, don't just state results. Let's summarize today's lesson. The key points to remember are, first, current creates magnetic field. Electric current flowing through a straight wire produces circular magnetic field patterns around the wire. This fundamental relationship connects electricity and magnetism. Second, the right-hand grip rule determines field direction. Point your thumb in current direction, curl fingers around wire, and fingers show field direction. This rule works universally for any wire orientation. Third, field strength decreases with distance from the wire. The field is strongest at the wire surface and weakens as distance increases following an inverse relationship. For further study, practice the right-hand rule with wires in different orientations, vertical, horizontal, and diagonal. Also review sketching field patterns accurately, showing circular field lines with correct spacing and direction arrows.